Now, if you remember from Rn, I mentioned that if you have 1 squared plus 2 squared all the way to n squared, what's the formula for that? What's the general formula for this series? Well, it's n times n plus 1 times 2n plus 1 all over 6, right? So notice that we're not going to n squared here, we're going to n minus 1 squared. And so to adjust the formula for that, basically what we can do is we can either subtract an n squared from both of these, because then the last term would be n minus 1 squared, right? So that's one way to go about it. Another way is to just change this last term to be n minus 1 squared. But then if we change this term from n to n minus 1, we got to change all of these terms from n to n minus 1. So instead of n here, we would have n minus 1. Instead of this n, we would have n minus 1, then we'd have plus 1. So the 1's would net out to 0, and then we would just have an n left. And then 2n plus 1. For the n, we're plugging in n minus 1, then we're going to have the plus 1, like that. And then the 6 stays as is. So basically, we would end up with n times n minus 1 times, if we simplify this, we would have 2n, and then we'd have minus 2 plus 1, which is minus 1. And that's going to be all over 6. All right? So this square bracket over here ends up equaling this. All I did was, instead of that n squared, I put n minus 1 squared, and then I put n minus 1 for all the n's in the formula. All right, so again, as I mentioned at the very beginning of this stuff, a lot going on. Like, this is a pretty tedious, pretty complex section. You may have to watch it a couple of times for stuff to sink in, but as I promised, stuff is going to start getting easier once we get into the integrals. So what I'm going to do now is plug in this for this square bracket. So this is going to be 1 over n to the 3. And then I'm going to write this for the square bracket. So we'd have n times n minus 1 times 2n minus 1 all over 6. Like that. Okay, so now notice this n and one of these n's cancel out. So what's the final expression going to be for ln? Well, the final expression now is going to be n minus 1 times 2n minus 1 all over 6n squared, like that. Right, so that's the final expression. Let me just make sure everything's all good. Yeah, it looks all good. So now, what's nice is this here is going to be the area of all of these rectangles with these left corners for this function between these x values for however many rectangles we choose. So remember when we did 4, what's L4 going to be according to this formula? Well, notice we would have 3, then we'd have 7, then we'd have 6 times 4 to the power of 2, and we'd end up with 7 over 32, which, if you remember, that's the value that we got for L4 when we did it manually. Now, what about L5? Because we also used 5 rectangles before. So if we plug in 5 for n, notice that we'll have what? 4. We'll have 9, 6, 5 to the power of 2, like that. So this would end up being what? 36 over 150. Right, 25 times 6. So what's this going to reduce to? This is going to reduce to 12 over 50, which this is going to reduce to 6 over 25. And if you remember, 6 over 25 is also what we got for L5. And so what's nice about this expression here is that we can get the value for the sum of all of these rectangles for any number of rectangles for any n value. Right? So we could plug in, if we use 9 rectangles, we could plug in 9 for n. If we use 1,000 rectangles, which would be really close to the exact value, we would just plug in 1,000 for n. And if we want to get the exact value, just like we did with Rn, the exact value or the exact area is going to be as n approaches infinity. Right? As we have an infinite amount of rectangles here, this space, right, that excess space is going to start to minimize, and these rectangles are going to get closer and closer to the curve, right, the more rectangles that we use. So we would just find the exact area of, or we would find the limit as n approaches infinity of Ln, right, to get the exact area, or Rn. Right, I'll just write it over here. Both of these, no matter which expression you get, both of them are going to give you the same thing. So working with this here, what I'm going to do is, like I did before, I'm going to expand that numerator to n. Actually, you know what? Let's go about it in a different way for this one. I expanded it when we dealt with Rn. For this one, what I'm going to do is I'm actually going to factor out an n from both of these brackets. So if I factor out an n from this bracket, I would be left with 1 minus 1 over n. And then if I factor out an n from this bracket, I'd be left with 2 minus 1 over n. And this is going to be all over 6n squared. Well, notice n times n is n squared, so this, and that would cancel out. And then notice that this is going to go to 0, this is going to go to 0, so we'd have 1 times 2, and then we'd have this 6 at the bottom, 1 over 3. Right, so whether we use Ln or we use Rn, when we take that limit as n approaches infinity, we're going to get 1 over 3 each way. And if you remember, it's erased now on the board, but when we dealt with Ln, because this last rectangle, the height was at this point, we were using, like that last expression was n minus 1 to the power 2, so we had to adjust the series formula. And that's why I was saying Ln, I feel like, is a little tougher to deal with than getting an expression for Rn. Because Rn, it was just 1 squared plus 2 squared all the way to n squared. We could just nicely plug in that formula in terms of n. But because for Ln it was up to n minus 1 squared, we had to adjust that formula, right? So that's why I feel like Rn is easier to deal with, but you're going to have to know how to deal with both. All right, so that's basically the process, right? So you're going to have a function, you're going to have a certain interval, and then you're going to have a certain number of rectangles. Sometimes the question is going to tell you how many rectangles to use. They're going to tell you whether they want left points, right points. You could also use midpoints. I'll do an example on that as well. But yeah, stuff can get pretty complex because these intervals, like this one wasn't bad because it was from 0 to 1. But what if it was from like 5 to 7? Right? Then things start getting a little bit more tricky, especially when you're dealing with the x values in between, getting expressions for the x values, and you could deal with more complex functions. So this stuff can get pretty complex, but I feel like these fundamentals that we just went over with this example is very important.